Okay, so I want to talk about DTN security key management, which has actually been alluded to several times already today. Next chart. So we know already that we've heard today that the internet protocols, they're ubiquitous. They're most widely deployed networking protocols that have ever been involved in computer networking. They're the backbone for all data communications in the global network. But they're best suited to well-behaved paths where we have low to moderate end-to-end delays, low to moderate packet loss and reordering, and per packet queuing delays and network middle boxes that are, again, nominal. Good for conversational data exchanges, client-server architectures, reactive congestion control, end-to-end flow control. But let's go to the next chart. But we now have new requirements emerging that don't fit that same mold, where we have moderate to long end-to-end delays, many minutes, hours, or days. Moderate to high end-to-end packet loss due to significant disruption. Moderate to high queuing delays, open loop data exchanges instead of conversational data exchanges. So these use cases are not always satisfied well by TCP/IP. We have use cases such as space-based communications, satellite-assisted communications for ground stations, civil aviation, where we might have loss of comms and need to do bulk transfers, unmanned aerial systems operating in remote regions, and many other emerging use cases that we've seen. And DTN provides a practical solution for this. Next chart. So DTN space-based communications, DTN replaces customized non-standard communications between International Space Station and ground systems. It overcomes limitations of RF space links, as we've heard already today in several other presentations, the TDRS availability issue, communications latency, and ground TDRS ISS RF links. DTN is compatible with deep space communications. One-way light time from Earth to Mars is at least 4 minutes minimum. Satellite assists are not always available, so we oftentimes have long outages. DTN provides space system support for isolated ground systems where data exchanges are only possible during certain satellite overflights. But DTN needs well-architected security solutions. Current security is based on piecemeal solutions, whereas we need delay disruption tolerant security standards, such as emerging from the IETF currently. Next chart. So the DTN for the International Space Station, the ISS is like an internet unto itself. It's got onboard network devices connected as a private internet network, separate from the Earth-based internet, and separate routing and addressing domains. We have well-connected onboard devices, but communications with off-board control stations are subject to TDRSS availability. So we need DTN security solutions to secure onboard devices, and in particular, we need DTN security key management solutions to help make the security solution secure. Next chart. So we have published a document in the IETF called DTN Security Key Management Requirements and Design. And some of the requirements that we've specified in the document are listed here. The solution must not rely on online access to a public key infrastructure because low delay online access might never be available. So even if the key is retrieved from the PKI system using some delay tolerant poll system, it might get there long before the time to decrypt the data has gone by. So the traditional PKI systems are incompatible with DTN. The solution must ensure that security keys are put in place before they're actually needed. Otherwise, the bundle would be rejected due to security policy. It must be based on trust anchors common to all DTN nodes, because DTN nodes can't simply assert public keys directly to one another. Otherwise, the network would be inherently insecure. It must be based on a published subscribe model. On-demand retrieval from a traditional server is not delay tolerant, as we discussed before. It requires one or more key authorities to publish bulletins to which all DTN nodes subscribe. So the bulletins need to reach all DTN nodes in the network over the same long delay links that would carry ordinary data packets. Bulletins have to be published, therefore, at some time in the future before the keys are actually needed. Next chart. It must not introduce a single point of failure. So all DTN nodes can't simply accept a monolithic bulletin from a single key authority. Because what if the key authority itself fails? Or what if it's hacked? Or what if it begins sending erroneous data? So that means that they must distribute the key distribution service among multiple key authority nodes. The key authorities have to agree on a bulletin through control message exchanges. That's not a delay tolerant function, but it doesn't need to be as long as the key authorities are within the same low delay bounded network. Each key authority publishes a few overlapping pieces of the bulletin, and that way, no one single key authority becomes a single point of failure. And each DTN node receives the pieces of the bulletin and reassembles them into a complete bulletin. So in that way, it's okay if one or more of these key authorities fails because the pieces are overlapping and the nodes will still be able to construct the bulletin. It's okay if one or more of the key authorities has been hacked because the integrity of the bulletin will be asserted by the consensus agreement of the remaining KAs. But it's not okay if all key authorities fail or become compromised. At least a few non-compromised trust anchors must be present. So also we must ensure that the key distribution service is highly available and hardened against compromise. But that's not really very much different than any other critical infrastructure in the internet today. Things like online certificate authorities, the DTN, the domain name system itself is another example of critical infrastructure that has the same kind of characteristics that we're looking for of the key authorities. Next chart. So we have this idea that came originally from Scott Burley called the DTKA, Delay Tolerant Key Administration Service. It's based on distributed key authority nodes that provide bulletin services to DTN clients. There's a prototype implementation in ION. We in Boeing have been working with that implementation for some time now. It's not yet released for public access, but in Scott's presentation, he announced a potential release candidate for that function. The key authority nodes multicast bulletin segments that all DTN nodes on the International Space Station and on Earth receive. The bulletins include the future public keys of all DTN nodes. So I liken this to back in the days of the ARPANET, where SRENIC was a service that had all of the host name to IP address mappings. And that got sent out as a bulletin so that internet hosts could have the addresses of all nodes. And that was kind of the beginning of how internet naming got started. DTKA provides a similar function where we have a bulletin that contains all the keys of all nodes in the network being multicast to all DTN nodes. Next chart. So DTKA technical background, the security model for DTN is based on ephemeral session keys that are encoded with each bundle. It assumes that the security keys are ephemeral, that is, each DTN bundle carries a one-time use key, and the DTKA public-private key system is used to encrypt or decrypt the ephemeral key. So once we have the ephemeral key exposed to the node that needs to interpret the data, we can then decrypt or authenticate the data based on that ephemeral key. So that's the purpose of the public-private key, is to either authenticate or encrypt the ephemeral key. The DTKA is organized as a group of N key authority nodes, where each node has all current public key information from the network. Each DTN node generates its own public-private keys and sends them to each K authority node. And DTKA issues key assertions or revocations and bulletins sent to all DTN nodes. Next chart. Okay, DTN nodes use keys that they have received in bulletins based on bundle creation times. So they keep track of recently received keys for each node that they need to accept data from. And use the newest key that is no younger than the bulletin creation time. Since multiple keys are kept with creation times, no need to synchronize transmission and reception key selection. And nothing in the key distribution system is secret. It's all public information. So the result is that all public keys get distributed securely, key management is automated, There are no multi-message exchanges over long delay links. We have these ephemeral keys that we use that are accompanying each bulletin, and no single point of failure or compromise. That might be it. Is there one more? Okay, so actually there are a couple more. So some practical deployment considerations is that DTKA is based on multicast. So we require a scalable, reliable multicast capability. The bundle protocol reliably delivers bundles to one or more recipients. Reliability is based on convergence layer protocols such as TCP and LTP. And reliable delivery is hop by hop. Each hop needs to take custody from the previous hop to ensure that end-to-end delivery is reliable. Multicast reliable delivery is also based on hop-by-hop convergence layers, but large-scale reliable multicast is an end-to-end consideration. So one of the considerations we have for DTK is how does it scale? Does scalable reliable multicast really work over large DTNs? The security of the key authorities is a fundamental requirement, and again, it's the same as for some of the core internet services like the DNS. The system is resilient to one or more elements being compromised, but if you bring down all of the key authority nodes, it's the same thing as bringing down the DTN. But history has shown that services of this nature can be protected against comprehensive destruction. So it would take a massively coordinated event to bring down the DTKA key authority nodes, and I'll show that in the demo that's going to follow. Okay. Dealing with nodes re-entering the DTN after a long time away. How do you get those nodes synchronized again? DTK and mobile networks, we still haven't really gotten a handle on that. With DTK for the ISS, we continue working with Boeing, BDS, and NASA partners to understand the operational limitations of the environment and determine a best layout of the DTK critical infrastructure to service the ISS. That might be the last one now. Maybe not. So in summary, the International Space Station is like an unit unto itself. Traditional PKA services are not delay tolerant and not candidates for operation in DTNs. DTK is the core engine for publication of public key bulletins, and practical deployment considerations for DTK are subject to ongoing work. But our goal is to adapt the DTKA-like approach for securing the ISS. Next. Okay. So what I would like to do now is switch to a live demo of the DTKA system in operation. Oh wow, it worked. Okay, so what you're seeing right now is what's known as a core model. Core is a network modeling system that's based on lightweight virtual machines. So each icon you see in this diagram is a little virtual machine unto itself. It runs its own operating system kernel, it runs its own networking protocol stack, and it's a lightweight virtual machine running on a single Linux laptop. So I'm going to start the emulation. What we see now are the nodes starting up, running their protocol stacks. Now they're up. And what I have represented in this diagram is a set of DTKA key authority nodes, all within close communications range of one another. By that I mean within a few hundred milliseconds delay-wise. I have this notional interplanetary coordination backbone that connects the key authority nodes to DTN networks here on Earth, a DTN network on the International Space Station, and a DTN network on Mars. The link between the interplanetary communication backbone and Mars has a delay assigned. So Core is able to insert delays in packet transmissions. So for example, on this I have 5 seconds set as the delay. Normally for Mars you'd set about 4 minutes, but this is for demonstration purposes. Now what's happening right now is that these DTKA nodes are sending bulletins that are received by all of the key authority nodes. And you can see this update right now is a multicast transmission of the bulletins from the key authority nodes out to the client nodes. So if I go to the client nodes, I can see that the icons are blue, indicating that they have recently received a bulletin from the key authority nodes. And what that means is that their list of public keys for all nodes in the DTN are up to date. And you'll see as the colors change, they're getting staler and staler, but the DTKA nodes are going to update those bulletins before they become timed out to the point that the keys are no longer usable. Now, if I were to go to one of the key authority nodes and shut it down, you'll see what will happen is it'll drop out of the key distribution or key discussions. I'm forgetting the word. The consensus agreements between the key authority nodes. But even though that node has been taken out, you'll see that the clients are still getting their public keys because the 5 key authority nodes that are left over are able to continue without the one that's been taken down. Now let's see what happens when I take down a couple more nodes. Now, when I take down one of these key authority nodes, this is actually a very significant event. This would be akin to somebody launching a terrorist attack against a heavily secured and guarded building. So this is not something that would happen just because of a software fault or somebody kicking a cable or something like this. These are highly secured, highly robust devices. So once again, compromise of one of these key authority nodes is actually a fairly significant event. But if I take a couple more of them down, we should see that the keys are still being updated because there are still enough of the key authority nodes left that they can have their consensus agreements continuing even though we've had some of them that have been compromised and taken down. So just to verify that, we'll wait till this group of Earth-based terrestrial nodes goes purple again. Now if I take down one too many of those key authority nodes though, if I'll take down another one, what we'll see happen now is that there's no longer enough K authority nodes to have consensus agreements, and we'll essentially just have the bulletin publication process fail to the point that the client nodes, the client DTN nodes, are no longer going to be getting their key updates. And you'll see what happens is that the keys become stale. They'll go through several progressions of staleness until they become unusable. So let's bring another one of these nodes back up again. Okay, so now that we've got 3 of the 6 back up, eventually, and this takes a little time because we have to get things synchronized again, these nodes will turn from red back to purple again, signifying that they're again getting their key bulletins. In the meantime, I'll show you one thing that can be done with this model to prove that we're actually running DTN nodes. I can pull up a terminal window on one of these icons. Okay, now you can see that the keys are being distributed again. And I can use ION commands like bping. I got a typo. So I can use ION type commands from any of these DTN nodes to talk to any of the other DTN nodes in the network. And if I tried to contact one of the nodes on Mars, you'll see what happens is that I won't get a response back for a long time. That's because we have a long end-to-end delay from Earth to Mars. But will essentially happen soon is that we'll start seeing the replies coming back after long delays, and they come back in bursts. So this is where we have DTN operating over links that TCP can't operate over. Well, I could play with this a little bit longer and show you some more functions, but I think that's about all we need to show for the demonstration purposes. Any questions at all?
Hi, Scott Pace. I have maybe possibly a dumb question, but with regard to the key network, how do you handle the precision time transfer? Where is it getting time from? On boards, is it getting it from GPS? How is it synchronizing itself to handle the keys?
Well, when we talk about the key authority nodes themselves, they all have to be within the same low delay connected network, like the Earth-bound terrestrial network. And then you can use traditional mechanisms like network time protocol to synchronize the nodes. So the key authority nodes, you can't have some of them be on Earth, some of them be on Mars, and have all of them having to synchronize with each other over that Earth to Mars link. Now you can have a set of key authorities on Earth that all deliberate over a set of keys, and a separate set of key authorities on Mars that deliberate over a separate set of keys. But if you had all key authority nodes that deliberate over the same set of keys have to be within the same low delay environment.
Okay, so you basically have communities of time and communities of time.
I think Scott might have a better answer to that, but that's essentially right.
Yeah, just to say a little bit more on that, the intent of the key distribution design is that the effective time is attached to the key when it's sent out is not applied to what the real time is, it's applied to the creation time of the bundle. So the sender and the receiver, because they're both using the same key that's associated with the same effective time, they're going to use the same key, and it'll decrypt or whatever effectively, even if the time is incorrect at the receiver, because you're just working off a label, right? So it's sort of an arbitrary thing. At the same time, it is supposed to be fairly close just to be able to make sense of things, because if the time on the bundle is 2 years ago and it was sent yesterday, that's sort of not going to make sense in the operation of the network. There's a degree of time synchronization that is needed anyway to make the system work. In our experience, when we ran the DINET experiment, we had time disparity on the order of 8 to 10 seconds, and it was fine. The granularity of time in functions like the time to live on bundles in the bundle protocol spec is at 1 second granularity. So precision timing is, first of all, sort of structurally not a real problem, but in addition to that, if you're off by a number of seconds, really, 8 seconds, 10 seconds, perhaps even 20 seconds, the network is likely to work somewhat less efficiently, because you'll be initiating and terminating contacts not at the right time, but a few seconds off. So you're missing some transmission opportunity or some reception opportunity. But there's nothing catastrophic about it. It just degrades sort of gradually.
So you had mentioned that the key authorities are all on Earth within hundreds of milliseconds away from each other.
Yeah.
Is that a generic assumption that all key authorities would be on Earth, or if there would be key authorities anywhere else, and how would they interoperate?
Well, again, if there were key authorities on Mars, let's say we had an internet on Mars that was on the same scale as what we have on Earth. Billions of people living on Mars. We have billions of, hosts out there. Earth would have its set of key authorities that keep track of the Earth keys, and Mars would have its set of key authorities that keep track of the Mars keys, and they'll exchange that information with each other over the long delay link. But the synchronization of the set of keys for each domain is maintained locally within that domain. Does that make sense? Or
No, that makes sense. I see
Okay.
how that would work. And another question, so you said key authorities being in secure locked facilities, and I
Yeah.
completely understand that. As far as, and you also mentioned about the next steps of trying to put this on ISS, what does that mean as far as setting up enough key authorities here on Earth in order to satisfy using this on ISS? What type of effort is that going to take?
Well, that's a good question. I don't know enough about how the ISS is coordinated from Earth-based stations. I understand that there's the Johnson Space Center in Houston. I don't know to what degree other NASA installations like Huntsville, Alabama might also be involved. But those might be candidate locations to stand up a key authority.
Will it work with two? Because you showed when it came down to two left, it didn't work.
Scott might have the technical explanation for that.
I was just going to, okay. I was just going to suggest that, for example, you might have one of the key authority machines at each of the DSN stations. So now you're spread 120 degrees apart around the world. So there's 3, and maybe Johnson, Goddard, JPL. That would give you 6, which is what we're showing here. And that's probably pretty good coverage. Yeah.
Yeah.
Again, that'd be a coordinated effort for ISS.
It'd be challenging, right? Several continents.
So it's Vince Cerf again. Back in the 70s, what you call a key authority would have been called a key distribution center at the National Security Agency. And this reminds me, what you described, and I'm sorry I had to go out and take another call, but what you described reminded me of the host.txt files from years ago where we would distribute the IP addresses of hosts until the DNS was needed.
Right.
The thing which I did not understand, it was not the part about the distribution, it was the obtaining the public keys in the first place, because it's clear they have to be generated in pairs. One of them is the private key, the other is the public key, and presumably you are not generating public and private key pairs at the key authority. They need to be generated by each one of the end nodes.
That's correct.
So
and then they get reported
somehow
in.
You have to get from the end nodes the public keys that they are now going to use in order to encrypt the ephemeral keys. So I didn't quite follow, I may have left at the point where you were describing this. Obtaining all that information before you could distribute the public key information, or alternatively, as it dribbles in from the various end nodes, that you assemble something with timestamps and other things to say, here is the latest information that I have about what public keys are usable. And now we get into this synchronization challenge, because the party who generated a public and private key pair presumably shouldn't use it until it is heard that the public key is known by the rest of the community. So it has to wait until you distribute the public key before it tries to use the private key that goes with it. Have I got that right?
Yeah, I mean, all of it's right on the money. The nodes themselves generate key pairs for themselves. They keep their private key to themselves, and they give the public key to the key authorities.
Right.
The key authorities then create a bulletin, craft a bulletin. In fact, one of the nodes that I should have showed earlier is actually generating a new public key every 10 seconds. And that's what keeps the engine kind of going. But so the keys are generated and given to the key authorities, and then the key authorities multicast the bulletin.
Yeah, I understand that. Every 10 seconds is kind of an interesting choice given the kind of dynamics that we expect the deep space environment to look like.
Yeah.
That sounds like overkill by a couple orders of magnitude.
I've told Scott that it's DTKA on hyperdrive. It's just for demonstration purposes. So.
Oh, I see. Okay,
Yeah.
so this is a caffeinated version of DTKA.
Yeah, exactly.
I got it.
Yeah.
All right. Well, the fact that you can show that you can actually do that makes sense. Last point, and that is that which is encrypted, the ephemeral key,
Right.
I would presume would be a symmetric key that's being encrypted as opposed to a public-private key pair, because the efficiency of the public-private key or the public key architecture is poorer than more general symmetric keys.
The ephemeral key itself is a symmetric key, yes.
Okay, got it. All right, so that's a classic design in effect.
Right.
Any other questions? Yes, I got 2 lined up. Oh, you're next. Man in the red shirt.
So related to performance, for the session key, are you able to use AES and NI extensions for performance?
Do you know, Scott, what the
AES, NI, for instance, the CPU extensions?
this gets down to the BSP.
Right. The way bundle security protocol works, you can have a very wide range of cipher suites, and so you can select whatever seems to be appropriate in that environment. So there can be many different cipher suites for bundle block integrity blocks and for block confidentiality blocks. So AES is certainly one of the options. I forget exactly what's implemented in ION right now.
Okay. The other thing that I'm curious about is just performance in general, whether this has been characterized, the idea of one session key unique per bundle and having to decrypt that session key each time you receive a bundle obviously is going to put a bound on your bundle size and bundle throughput.
So there's certainly an impact. We haven't done a lot of performance testing on it that I know of. What ought to mitigate that somewhat is that the ephemeral symmetric keys are pretty short. So decrypting, even asymmetrically decrypting something that short, there's an impact, but it's not necessarily a gigantic impact. And then the bulk of the overhead I would expect to be the symmetric decryption of the payload, which is very much larger. So it's a valid point, and we need to characterize it. It hasn't been done yet.
Yeah.
Okay, so this relies on the keys for each node being flooded to every node, as with host file in the old days.
Yeah.
We moved away from the host file because it didn't scale.
Right.
In terms of using the DTN for sensor swarms and Internet of Things and millions of devices, that sort of thing, is this a method that effectively won't scale in that use case, and another method would need to be chosen for that? So this is effectively a space-specific, low-density node method of doing security?
I can't give you any details, but I can say that we're looking into scalable solutions inside of Boeing right now. That's not to say that DTKA is not a scalable solution. What we are doing, though, is we're looking at some alternatives. What we think we have is something that will work well with the ISS for the near term. And when we get into large DTNs, that's when we're thinking that we're going to need to have an advanced solution that might have better scaling properties.
Thank you.
Just to say a little bit more about that, I think we have been talking about possibly having federations of these distributed key authorities so that you have multiple distributed key authorities that are generally co-located with the populations they serve, as Fred was mentioning earlier. It might even be finer scaled than planetary. It could be, one for Europe. It could be one for Kentucky.
Right.
Ultimately, if it's necessary in terms of scalability, for really closely co-located populations of nodes, it might make more sense for a designated node to be a local key server and be the thing that manages the list of all the keys, and everybody could ask it. As long as they're all within non-delay tolerant sort of distance, then that sort of query response client-server kind of architecture can still work. But at the same time, again, storage is becoming cheaper all the time. It might well be that storing all of the keys for 1 million nodes seems like an unreasonable thing to do, but if the keys are not that big, 1 million keys of 32 bytes, for example, is not necessarily a huge amount of data these days.
It's Vint again. I want to respond on the scaling side.
Okay.
As much as I hate to admit it, as I think more and more about the Internet of Things environments, sensor networks, and so on, I've reached the conclusion that hub-like architectures may turn out to be necessary just for management reasons, where the hubs have more capacity, more communications, maybe they even have more reliable power than some distributed sensors that are running on battery or solar or something like that. So that the hub is the item that manages configurations for and keys for and so on and validations for these edge devices. You could use the hub to outfit the edge device with the information it needs to validate communications that are coming to it. But to have tens of thousands of devices all participating in the distribution of keys in the way that you just described may not necessarily be a very effective way of making it work. It might not be adequately reliable either. So I think I'm reluctant to come to that conclusion because hubs and firewalls sort of fall in the same category of holy crap, why are you depending on this thing that you can work your way around? So it may be we'll end up with some devices that can work in the way you describe and others that have to be shielded by an alternative intermediary.
Definitely. Yeah, just turning back to my topology here again, Vint. Consider the ISS as a Internet of Things, if you will. Mm-hmm. And here we have one hub that's servicing all the onboard devices. And those onboard devices don't have to converse with the outside world. So yeah, we definitely get economies of scale when we can have things grouped around, clustered around a hub of some kind.
The thing which gets really complicated is you start with configurations that look like this, and you can imagine that the residential model of this is that you've got a bunch of devices at home, and they're all driven off of a particular hub. And then you move to another house which has another bag full of edge devices, and you're now trying to figure out how do I create the ensemble? Now I have multiple hubs, or how do I make this all work? It makes my head hurt, but we need to figure out how to do that because certainly in the residential setting, we're going to have that kind of things coming together unexpectedly. In the space environment, we may also experience some of this, maybe not quite on the same scale, but when you can imagine, as we have more and more mobility around the solar system, we will be moving devices, spacecraft and the like, from one environment to another, where they have to become an established element of the destination network.
Right.
Okay, other comments? All right, we're Mr. Master of Ceremonies. We're next. Thank you very much.
Thanks.